Welcome to a read along with Dr. Powell in the book Discrete Perspectives in Mathematics. This is section 7.1, complexity of algorithms. So, time complexity. Pretty much, we're just getting some kind of a measure of like the number of steps of an algorithm. There's different ways of thinking about the size of a step and what it means. And some of this paragraph right here discusses specifically for Euclidean algorithm how to think about number of steps. Is it like in the specific little operations that we're doing? For now, let's just think about the number of lines of the algorithm and our goal. Our goal is to find the greatest common divisor, perhaps. The greatest common divisor happens right here at this line, the line right before zero. And it's the last non-zero remainder. And you know that it's the last non-zero remainder when you get down to zero. So here we have 3 lines. Okay. So what we're going to do is think about worst case scenario or like the slowest this algorithm could go, like keeping these remainders as big as possible. In fact, not just a worst case scenario, but a worse than worst case scenario, something that's actually wouldn't happen, yet is worse than anything that does happen. And so we can kind of think about, well, the biggest a remainder could be perhaps is just less than maybe half of the bigger number here. So, roughly just one less than like the divisor here. So that means that worse than actual is still remainder even larger if this was exactly half of the bigger number. So you can kind of think on these imagine that we have maybe more lines here or whatever, but this guy right here at worst is half. So you can think of it, or worse than worse, is half than the bigger number. This bigger number actually was a remainder 2 lines ago up here, which means that this guy is about half of 2 lines ago, and this is at worst, or worse than worst, that is. So this would be 1/2 of what was here 2 lines ago, which means from line to line, we're actually looks like so every 2 lines we divide by 2, so every 1 line we would divide by square root of 2. So the result is better than if we divided by square root of 2 each time. So if we dividing, okay, we want to be able to get to the bottom line that has a 0 remainder. The remainder in the line before this one at worst is the remainder in the line before this one at worst is a 1. So then that means we just need to figure out how many times we need to divide by square root of 2, so we actually get down to 1. And then we just add 1 to that to have 1 more to get to 0. So that's worse than actual for sure, but it's going to be an upper bound for the number of steps. Okay, so then for sure what we could do is we maybe start off with like the first remainder and take what power of square root of 2 do you have to get up to that guy, because that's like how many square roots of 2 you have to multiply to 1 to get up to r. That's the same number of square roots of 2 you have to divide r by to get down to 1. Then you add 1. So this is like a nice upper bound here. All right. Okay, so we can imagine that the larger number n on this first line. Okay, so let's think about that for a minute. Now we're using r right here, but let's see, r is assumed to be worse than actually happens. First remainder, we can imagine that the larger number n on this first line is simply 2r. Okay, so like twice the remainder. All right, with this idea we can get a simpler bound. So this is a simpler bound if we replace this 1 by, so we do 1 more even than this bound right here. Okay, so go 1 more, even more. So this is even a bigger bound than this. So this already is an upper bound. Let's go to even bigger bound because it's nicer to write it. We'll see why. Because we can rewrite this 2 as, in fact, 2 is actually equal to log base squared of 2 of 2. Think about that. Square root of 2 raised to the 2 is 2. So this is like the exponent. You have to raise square root of 2 of 2. This is another way of writing down 2. Kind of funny, but it's true. So we can rewrite that, and then we can use properties of logarithms to put these things together. Log base square root of 2 of 2r. That's like saying log base square root of 2 of n, because we're assuming like n is equal to about twice the remainder. So larger numbers like 2 times the remainder in the first line. If we think of this worst case or worse than actual scenario, let's just get an upper bound. So really, it looks like we should expect that there are less than log base square root of 2 of n lines. And in our particular case, we actually, let's take a look at this. Let's see here, log base square root of 2 of 48. And so this right here is actually, that's our upper bound. Let's get something we can compute easily. This is bigger than this, of course, and we can compute this because 2 to the 5th is 32. So square root of 2 to the 10th. All right. So the upper bound is even bigger than 10, which is even bigger than the actual. So upper bound is too big, but that's what our goal was. We just want to find a nice upper bound for what's happening. So something more than what will actually happen. Okay. As we look at the remainder k in the course of the algorithm. All right. So what are we doing? We're counting the number of certain types of actions depending on the numbers that we start with. Notice, okay, so we started with n be like the bigger number. And we want to have a function that represents how many lines are needed for the Euclidean algorithm if n is larger when n is the smaller one. All right, maybe we want it to depend on both, maybe just on n, but it'd be some kind of function for an upper bound. So we want to kind of bound f of n m. Okay, so f of n m, we want to find an upper bound for it. And okay, the bound could determine n. Of course, the number of lines depends on both n and m, but an upper bound might just depend on one of them. Okay. So this function f of nm is not the bound, it's actually what's actually happening. And it's not continuous, it can go all over the place perhaps. However, we're going to bound it by a nice continuous function is kind of the idea. All right. And maybe it's only involves one of these guys, one of the inputs. Okay. So one of the most important parts of this process is decide what are we going to count. So up here we were counting just number of lines, and what it should depend on. Does it depend on both of them, n and m, or just n or something? Okay, that concludes that little subsection. Thanks for watching.